Welcome to Injection and Detection in HPLC. So let's now look at the hardware used to inject samples and detect solutes exiting the column. Note that detection using mass spectrometry was discussed in section 21.4 and will be largely ignored here. A pump used for HPLC needs to have a steady and reproducible flow. A fluctuating flow rate can produce detector noise, which will obscure weak signals. So this pump has two sapphire pistons, one here and one there, that provide a programmable constant flow rate up to 10 milliliters per minute at pressure up to 40 megapascals, so 400 bars or 6,000 psi. The solvent can be taken from up to 4 solvents via a 4-way valve, allowing for programmable gradients in our solvent mixture. The injection valve has connections for an interchangeable sample loop, so that's this loop here. The sample loop volumes vary from 2 to 1,000 microliters. And in the load position, which we have here, a syringe is used to inject sample into the sample loop. So we've got our fluid coming in here. It comes back to our 6-way valve and flows through and out to waste. The high pressure flow of the solvent passes in from the pump, through the valve, and back out to the column. And when our valve is then rotated, we get this case, and now any volume coming in from the needle is being shunted directly to waste, and now our solvent coming in flows through that sample loop, goes back through that 6-way valve, and then goes to the column. So we're effectively flushing our sample loop onto the column. Now, ideally, a detector is universal, which means it responds to every analyte. It's sensitive to low concentrations. It gives a linear response. It doesn't broaden the solute peaks, and it is insensitive to temperature and solid mixture composition. The detector volume should be less than 20% of the volume of the chromatographic band in order to prevent peak broadening. There is a pressure gradient from the pump to the exit of the eluate to atmospheric pressure. Since the detector is near the exit, the pressure has dropped to near atmospheric pressure. And a decrease in pressure can cause bubbles to form in the solvent. And such gas bubbles in the detector may create noise, so the pressure has to be purposely increased sometimes inside the detector in order to prevent that bubble formation. Now, the most common HPLC detector is the ultraviolet detector, and we have a schematic of a flow cell for it here. We've got our eluate coming in. It goes past a window, flows down this channel, and then it goes out there. Now we have our light coming in here, it's going down that channel where we have our eluate passing, and then it goes out to our detector. Now simple UV detectors use a lamp that provides a narrow emission line, for example, mercury vapor, zinc, or cadmium vapor lamps. More versatile detectors use a broadband source like deuterium, xenon, or tungsten, and a monochromator to allow a specific wavelength to be chosen. The system that we show here is a double beam detector that uses a polychromator over here to disperse the light, and it has 2 photodiode arrays instead of a monochromator, and this then allows collection of the entire spectrum for both the sample and the reference to be collected at the same time. So we've got a reference aperture here, and we've got our sample flow cell there. A fluorescence detector uses a laser to excite our eluate and measures fluorescence. And such detectors are very sensitive and selectively measure only those solutes that fluoresce. To allow detection of an analyte that does not fluoresce, the analyte can be bonded to a fluorescent or electroactive group. And such derivatization can be performed on the sample prior to chromatography or after chromatography but before detection occurs. An evaporative light scattering detector, shown over here, responds to analytes that are less volatile than the mobile phase. The eluate from our column enters at the top of the detector here. The eluate is mixed with nitrogen gas in the nebulizer here and is forced through a small bore needle to form a universal dispersion of droplets inside the drift tube. Inside the heated drift tube here, the solvent evaporates from the droplets. And then, after that solvent has evaporated, a fine mist of solid particles enters a light beam from a laser at the bottom of the drift tube here. So we've got our light source coming in there and then going over here to our photodetector. So the particles then scatter light from the laser, which decreases the intensity of light that reaches that photodetector. The detector response is proportional to the mass of analyte present in the beam. In contrast, an ultraviolet detector can provide drastically different signal responses for two different analytes at the same concentration if those analytes have significantly different molar absorptivities at that wavelength of interest. Another advantage is that there is no peak due to the solvent front, so the early eluting peaks can still be observed. A charged aerosol detector provides sensitive, nearly universal detection that is nearly proportional to the mass of the analyte. So the eluate and nitrogen gas enters the nebulizer at the top left here and there. The large droplets are drained to waste, so they're coming out down there, while the smaller droplets are going down this way into the drying tube. In the drying tube, the solvent evaporates, which then leaves an aerosol which contains around 1% of our original analyte. In the corona charging chamber, which is down here, a portion of that nitrogen gas, which was coming over this way, flows over a platinum needle at plus 10,000 volts to form N2 plus. And note that this process is similar to that for atmospheric pressure chemical ionization that was described in section 21.4. The positive charge is transferred to our aerosol particles then, and the charged place of the trap here prevents small mobile ions from reaching our detector, but the large aerosol particles are too massive to be deflected significantly by the trap electrodes. And the total charge reaching the collector, which is over there, is then measured, producing our detector signal. An electrochemical detector responds to analytes that can be oxidized or reduced. For example, phenols, aromatic amines, peroxides, mercaptans, ketones, aldehydes, conjugated nitriles, aromatic halogen compounds, and aromatic nitro compounds. A pulse electrochemical detector also allows for detection of alcohols, carbohydrates, and sulfur compounds. On the other hand, a refractive index detector is nearly universal, but its detection limit is around 1,000 times higher than that for the ultraviolet detector. A deflection type detector has two triangular compartments through which pure solvent or eluate pass, similar to these two. We've got our reference cell there where we have our pure solvent, and over here we've got our sample cell where we have eluate coming out of the column. Now, collimated visible light with the infrared filtered out to prevent heating of our sample passes through the cell and strikes a photodiode array over on this side. Now, when a solute with a different refractive index than the solvent enters the cell here, our sample cell, then the beam is deflected and different pixels of that array are irradiated. So note that the refractive index detector cannot be used with gradient dilution because the sample and reference cannot be matched during that gradient. Furthermore, it has a small linear range over a factor of around 500 of solute concentration. Now, the main advantage of a refractive index detector is that it responds to analytes with low ultraviolet absorption. Now, we can also use mass spectrometry, and I'm not going to go into a whole lot of detail because we've already talked about using mass spectrometry in previous chapter. For comparing mass spectrometry to high-performance liquid chromatography, atmospheric pressure chemical ionization and electrospray ionization are the most common ion sources. So, as discussed in chapter 21, atmospheric pressure chemical ionization creates ions from the analyte and other species in solution, while electrospray requires that the analyte already be charged while in solution. That was injection and detection in HPLC.